Swayam Prabha. Digital India. Educated India.
Welcome back to the third lecture for our Muffler Acoustics course. So in the last lecture we just derived the continuity equation, was usually found in text on fluid mechanics and also in acoustics. So we see here the form of the continuity equation is this, and this is one dimensional of course, and when we expand this thing out you get something like this. So this entire thing. Now I want to draw your attention before we begin the momentum equation, this particular term what I have encircled. Typically in fluid mechanics what we have, this term is basically also called the total derivative, which is given by like this operator. So this comprises of the derivative or variations of a quantity with respect to time by at a fixed location, and here the variation, the spatial variation of a quantity at a given time, and u is the velocity in that direction. So this is called the total derivative also in fluid mechanics. So the equation, this equation, equation 2 can also be written in the following form, which is rho times rho so here you are. We will call this equation 3. Now we will probably go to the momentum equation, and to simplify the momentum equation you will make use of certain forms of the continuity equations, the expanded forms. So we now get to the momentum equation. We will again consider a cylindrical volume something like this, and let us identify in this cylindrical control volume what are the forces that act. First is the pressure, force by the fluid pressure, and let us say S is the uniform cross section area. So P S at x, and the other force that acts in the opposite direction is P S at S x plus delta x, and then there is also the force by the momentum influx. So the momentum influx, let me write with a different color, is rho u square s at x, and there is also a momentum influx at P rho u s at x plus delta x. All right. So before we proceed further, let us understand where are we getting this term from. So this can be thought as rho s times u into u. So something like rho times q into u. So this is like this has units of force, kg meter by second square. So and this is like your mass, it is like your volume velocity. So this entire term is like the mass per second. So mass by second in velocity that has units of force. So you have your momentum influx that is coming from the phase 1 say, and here you have phase 2. Similarly, you also need to, by balancing out the forces that I am going to do in the next slide, we can end up with the momentum equation. So, here we have Ps times x minus, so this acts say in the positive x direction and the other force is in the negative x direction, x plus delta x acts in the opposite direction, and then you have your momentum flux rho u square s at x acts in this direction and rho u square s at this, it acts in the opposite direction. So, if we balance this, what are we left with? So, this is like your rho s delta x times velocity. So, that is your momentum, mass into velocity, and we need to talk about the time rate of change of momentum, isn't it? So, that is how we balance out the forces in the control volume. Now, let us simplify. We divide throughout by delta x and take the limit delta x tending to 0. That is to say, we consider a infinitesimal element. When we do that, we end up, and of course, we are considering a cylindrical prismatic element kind of. So, S is uniform, it cancels out. Basically, what we are left with is and this so we are dividing throughout by delta x and obviously by s, s cancels out, delta x we get this term. Why? Because x, we are taking delta x to 0, infinitesimal element. So, we arrive at the definition of a derivative. Same case is for this term, and this is what you left in the brackets. So, basically we transpose all the terms on the other side to get the following form. I have purposely put this thing in here, where this is capital P different from P tilde. This is the total pressure. When we linearize the equations, we will understand what is meant by total pressure. It is the sum total of the ambient pressure plus the perturbation pressure P tilde. So, we need to wait till the linearization happens. Before that, let us go back to this equation, and so we see this kind of a thing. Okay, let me name this as number 4, and let me expand out number 4 to get, and by this I mean this, and by this I mean this, that is partial derivative with respect to x and with respect to t. This here can be any quantity. So, here we have u t plus u times rho t, and then we need to employ a clever trick. We need to group it in terms of rho u. So, rho u times u x plus u times rho u x is equal to minus del p of x. Okay. So, now we have got the expanded form of the momentum equation in the terms of equation 5. Now, let us use these forms, either equation form 1 or form 2, to further simplify the momentum equation given by 5. So, we will write down this in a little more clean manner. Notice that the term u here and u here, this is common, and here rho is common and rho is common. So, this is important because then you can actually group it u t plus u times u x plus u times rho t plus rho u x this entire thing is equal to minus del x of p. Now, I would like to draw your attention here. This equation, the one that I have encircled, is nothing but the continuity equation written in the form 1. This is nothing but your rho t plus rho u x is equal to 0, isn't it? So, since we do not have any sources, the term is homogeneous, this entire thing goes away. So, leaving us with the following term u t plus so this is what we get, and this again can be simplified further if you recall the definition of total derivative in terms of here is equal to minus times this. Equation 6 or equation 7. So, basically the simplified form of the momentum equation then is given by equation 6, rho times u t plus u into u x is equal to minus del x of p. So, we have derived the momentum equation, which we will also find in standard fluid mechanics text, and the continuity equation as well. And now what is remaining is the equation of state, which relates basically your pressure and density through some function. So, let us talk in detail. We will keep this equation 6 as well as equation 2 would be of importance to us. We will keep these equations aside. So, in the meanwhile, what we will do is that focus on equation of state. So, here you have your equation of state. So, instead of using conservation equation, we are using the equation of state, and one well known equation for a perfect gas is that T pressure is universal gas constants times density times the absolute temperature T, where R is typically your 287.08 joule by kg by Kelvin. So, this is the perfect gas equation which relates the pressure and temperature, but another form of equation which is often used and particularly useful in acoustics is some generalized relation between the pressure as some function of density and the entropy per unit mass. So, P is a function of density rho and entropy. So, when the losses are negligible, which is usually the case in acoustics, entropy remains constant. So, what we essentially have is an isentropic condition, that is the pressure is a function of density alone, in which case it becomes P as a function of density. All right. So, for most gases, the form that is usually used is the isentropic equation, which I am going to talk about now. So, let us say P naught is the pressure at a certain state and P naught and P is the pressure at another state. So, we can relate these two states by the following relation. P by P naught is rho by rho naught times gamma, where gamma is the adiabatic gas constant for air is 1.4 for air, dry air, and P naught is static pressure and rho naught is static density. All right. So, This equation, I would say this is equation 7, is particularly useful for gases. For liquids, equation number 7, isentropic relation may not be applicable. A more general approach is required in terms of the condensation factor. We will probably not go into that now, we will probably stick to the isentropic equation, which basically relates the pressure and the density at a certain state. P naught and rho naught are may be considered as an operating point or static point, and what we are really interested in is that how does small changes in pressure are related to the small changes in density. So, for now what we are going to do is define a quantity called c square, which is your nothing but sound speed, a very important quantity in acoustics. That is a quantity which tells you how acoustic disturbances propagate. So, sound speed squared is given by partial derivative of the total pressure with respect to the density at the constant entropy. S is constant. Now, since S is constant, partial entropy, we have only one variable, rho. So, C square is this thing. Now, another useful simplification will arise when we consider the total pressure P as decomposition of the ambient pressure P naught plus P tilde. P tilde is nothing but the acoustic pressure, if you recall the first couple of lectures, that is acoustic disturbances. So, I want to point out here that this P tilde is basically your small perturbations is something that hits your eardrum. When you are watching this video, when the sound is being emitted from the loudspeakers of your device, laptops or whatever. So, it is basically disturbances are created in the pressure in the medium air between your device and your eardrum. So, these pressure fluctuations are hitting your eardrum. The noise, that is the disturbances that are created by the device, they are hitting your eardrum, and that is what is causing the sensation of sound. So, it is basically this P tilde is what we are after. So, this is what we are interested in acoustics, and as you can appreciate, when you do this linearization, we just begin the process of linearization. Obviously, a lot of things have to be done in the momentum and continuity equations, we just begin. So, P tilde is your acoustic pressure, and that is what we are going to relate to small changes in density, which is given by your delta rho, or you can probably write this as rho tilde, which is nothing but total density minus the ambient density, rho naught. Okay. So, basically what is happening is that if you revisit equation number 7 and substitute these relations, let us call these relation as relation number 9 and substitute relations 9 and 7, what we get? What do we get? P naught plus P tilde, the acoustic pressure divided by P naught is equal to delta rho plus rho naught times rho naught times gamma. So, 1 plus P tilde divided by P naught is 1 plus delta rho by rho naught the power gamma. Now, if we apply our binomial theorem or expand this out, you get nothing but rho times delta rho by rho naught square plus HOT. So, HOT means higher order terms. Okay. So, then what happens is this goes away, this goes away, and what we are left really is P tilde divided by P naught is equal to gamma times delta rho by rho naught plus their higher order terms, which we will probably ignore, including we will probably ignore these terms and we will focus only on the small order terms, which is gamma times P naught by rho naught. You can also write this as, of course, like I said, P tilde divided by rho tilde is equal to gamma times P naught by rho naught. So, this is equation number 10, and actually you can put this as C naught square. So, if you recall equation number 8, this was for the generalized sound speed, basically not necessarily evaluated at the operating condition given by P naught or rho naught. What I mean to say is that the relation between P naught and rho naught is not linear, it follows the isentropic law, but for small changes in acoustic pressure, that is basically small signal equation, strictly only for small signal equation, this relation P tilde by rho tilde, small disturbances, the sound speed or disturbances propagate at constant rate, that is given by gamma times P naught by rho naught and is denoted by C naught square. Suppose if the signals are no longer small, as it happens in the amplitude of disturbance is no longer small as it typically happens in nonlinear acoustics, the sound speed may not be constant, it depends on the complete process. But usually for small signal equations, we can consider P naught as equivalent to atmospheric pressure at that point and rho naught to be the ambient density. So, once we substitute those values, let us see what is the typical value of sound speed squared or just a sound speed. So, if you put gamma value 1.4 for adiabatic constant and ambient acoustic pressure, which is 1.013 approx times 10 to the power 5, that is 1 bar, and 1.2, that is 1.2 is the ambient density, as you will see from this thing, 1.2 kg per meter cube. So, once you simplify, C naught is square root of whatever value you get. Let us do some quick calculation. We get something like 1.1818 10 to the power 5. So, we get something like 343 8 meter per second. You can probably put it as well 344 meter per second. So, this of course is at standard temperature and pressure, which is 20 degrees temperature, normal temperature and pressure, and sound speed can also be related to the temperature as gamma R T, where T is the temperature in absolute value. So, clearly C naught is proportional to the square root of the absolute temperature. For colder regions or where the temperature is dropped, sound speed will propagate at a slower rate as compared to the cases where temperature is high. So, the value that you saw here 344 meter per second, this was at 20 degrees based on the 1.29 thing. Similarly, when you have a colder thing, the density of the air is a bit higher, and then you will have typically a lower value of sound speed. So, basically this is the relation then, and now what we can do using our aim then is to basically use these relations, equation number 10, substitute that in the previous equations for the simplified equations for the continuity momentum, and further linearize it based on the conditions that we set about, that is basically your equation number 9. So, what we will do is basically, first of all, we will write down this as P times this. Let me call this as equation number 11, and we will put that equation number 11 in equation number 6 as well as equation number 2, and go about simplifying things. Let us begin with the continuity equation and see what are we getting. Let us first linearize it. So, I need to write down this equation, equation number 2, which is this. So, before we begin the linearization, an important thing to be mentioned here is that rho tilde, that is your small changes in the acoustic density, which is nothing but your total density minus the ambient density. This value rho tilde is much smaller than the ambient density. That is to say, rho tilde divided by rho naught is much less than 1, or well, rho tilde is much less than rho naught. Similarly, we will also find, well, actually there is one more thing. This condition leads you to the condition that P tilde should be much less than rho naught C naught times C naught. So, this particular quantity is very important. It is called the characteristic impedance. We will talk about that after some time, but before that there is another restriction, that is the particle velocity should be much less than the sound speed. So, basically you have this and this thing. So, the acoustic density perturbations, rho tilde should be much less than the ambient density, or the acoustic pressure should be much less than the characteristic impedance times the sound speed, as well as the particle velocity should be much smaller than the acoustic sound speed, or the sound speed just generally, disturbance speed at which the disturbance propagates. Also, important thing to be noted here is that the characteristic impedance rho naught C naught is significantly different for water as compared to air. So, generally people tend to believe that small disturbances, small acoustic disturbances in pressure should be much less than the ambient pressure, but that might be true for air, but for water is very different. What I mean to say is that the condition P tilde divided by P naught much less than 1, while it is obvious, but the more fundamental condition is P naught is much less than rho naught C naught times C. So, if you put in the values for air, you will see both the equations will pretty much give you the same things, but for water it will be very different. The thing is that this is approximately 413 and this is again 343. So, this is approximately of the order 10 to the power 5, well 1.4ish times this thing, and this of course we know to be 10 to the power 5, 1.013 something like that. So, they pretty much give the same restrictions for air, but for water it is very large. Anyhow, we will come back to our discussion on in air, and we will begin the linearization process in the next lecture. Thanks.